Today we're going to talk about the combined and basic gas laws. So we're going to be looking at 4 different equations, but they all are derived from the combined gas law. When we are looking at all of these gas laws, we are going to be looking at different units and different variables that affect how gases act. So we're going to be looking at pressure, volume, and temperature. Now the combined gas law is going to be including all of them. So the combined gas law is P1V1 over T1 is equal to P2V2 over T2. Pressure is P, volume is V, and temperature is T. Temperature, we are always going to use Kelvin as our units. Volume, we can use milliliters or liters. And then pressure, we can use any of the 4 pressure units that we've spoken about. So that's atmospheres, kilopascals, torr, or millimeters of mercury. And so, like I said, this is our combined gas law. And what we're going to be doing with it is comparing initial conditions to final conditions. So our initial condition is everything that's going to go on the one side of the equation. The final condition is everything that's going to go on the 2 side of the equation. So 1 is how our gases look in the beginning, and then 2 is how our gases look when we change them. This equation is referenced for you in your reference packet. I just took a snapshot here, but if you go to the formula page in your reference packet, you will see the combined gas law there for you. All right, so moving on to our next gas law is Boyle's gas law. And Boyle's gas law has us looking at pressure and volume. So what we can do is we can take our combined gas law, that's the one given to us in our reference packet, and because we're only looking at pressure and volume, that means that temperature is not changing. And so that means that in order to get Boyle's gas law, we can simply erase the temperature variable. And so Boyle's gas law is P1V1 is equal to P2V2. And so when we're looking at this equation, we have to be able to solve it, but we also need to know the relationship between pressure and volume. If we have a pressure of 1 atm, and we say that we're changing it to 2 atm, so we're increasing our pressure, in order to keep this equation mathematically equal, we are going to have to lower our volume from going to volume 1 to volume 2. So what this tells us is that pressure and volume have an inverse relationship. Okay, pressure and volume have an inverse relationship. Next up is Charles' gas law. And Charles' gas law is looking at volume and temperature. And so, again, we can start with our combined gas law. P1V1 over T1 is equal to P2V2 over, this should be a 2, over T2. And because we're only concerned with volume and temperature, that means that our pressure is not changing in those types of problems. So we can get rid of the pressure variable. And so Charles' gas law is going to be V1 over T1 is equal to V2 over T2. Now, looking at this math equation, because our variables are divided by each other, that means that they're going to have a direct relationship. So volume and temperature have a direct relationship. Okay. The last of the 4 gas laws that we are talking about today is going to be Gay-Lussac's gas law. And this one is going to be looking at our last 2 variables, which is going to be pressure and temperature. Again, if we start with our combined gas law, P1V1 over T1 is equal to P2V2 over T2. We can go ahead and get rid of our volume unit because Gay-Lussac's law is saying that volume is staying the same and only pressure and temperature are changing. So we can get rid of our volume. And so then Gay-Lussac's law is P1 over T1 is equal to P2 over T2. And again, in order to keep this equation balanced and true, we need to know that pressure and temperature also have a direct relationship. Which means that if the pressure increases from beginning to end, the temperature will also increase from beginning to end. So we're going to talk a little bit more about this, but what you're going to have to do is understand these relationships, and those have been written out for you. And then you're also going to have to mathematically solve these equations. So when we're solving these equations, the first thing that we need to know is what is being given to us in the problem. And a good organization tip for solving these problems is to kind of set up a data table. So the way that I always do it is I set up a PVT, and then I put a 1 and a 2. And so as I'm reading through my problem, I can fill in all of the different numbers that are given in the problem so that I know how to approach the problem. And I'm going to use it in the next couple of problems that we're doing. Okay, so the first one says a balloon contains 30 liters of helium gas at 103 kPa. What is the volume of helium when the balloon rises to an altitude where the pressure is only 25 kPa? So what I like to do is always set up my chart. So 1, 2, PVT. And then I read the problem and I go ahead and figure out what variables are given to me. So it says a balloon contains 30 liters of helium gas at 103 kPa. So those two go together, and that's going to be where it's starting. So liters I know is a unit of volume, and kPa I know is a unit of pressure. Then it says, what is the volume? So it's looking for the second volume when the balloon rises to an altitude where the pressure is only 25 kPa. So I know that I'm looking for my second volume, and they gave me a second pressure. And that was 25.0 kPa. They did not say anything about temperature, so we can assume that it remains the same, so we don't need that in our equation. So what we're going to do is our combined gas law is P1V1 over T1 is equal to P2V2 over T2. Since we don't have temperature in this problem, we can go ahead and get rid of the temperature part of our combined gas law. And so we end up with P1V1 is equal to P2V2. So now it's a matter of plugging in our number and solving for the unknown. So we have a first pressure, so that is going to be 103 kPa. We have an initial volume, which was 30.0 liters. And we have a second pressure, which is 25.0 kPa. And we have a second volume as our unknown. So that is the what we're searching for. So in order to solve for x, we need to divide away from it. So we are going to divide both sides by 25 in order to get our answer. We do 103 times 30 divided by 25. We end up with an answer of 123.6. And because our first unit of volume was in liters, our second unit of volume will also be in liters. So this right here is our final answer, 123.6 liters. Let's go ahead and do the next one. says the balloon inflated in a room at 24 degrees Celsius has a volume of 4 liters. So I know that I have a temperature and I have a volume. Then it says the balloon is then heated to a temperature of 58 degrees Celsius. So I have another temperature. It says what is the new volume of the balloon if the temperature, oh, sorry, this should say not temperature, that's my fault. If the pressure remains constant. Okay, I'm going to go ahead and draw my chart so that I stay organized. So we read that the pressure stayed constant. So I can go ahead and get rid of my pressure unit. It tells me that I'm starting with a volume of 4 liters. And it says, what is the new volume? So that is my unknown. It says that I start at a temperature of 24 degrees Celsius, and I'm heating up my balloon to 58 degrees Celsius. Now, earlier I said that we are only using Kelvin. So the first thing that we should do here is convert our degrees Celsius into Kelvin. So we know that in order to get to Kelvin, we do degrees Celsius plus 273. So for T1, I'm going to do 24 plus 273. And for T2, I'm going to do 58 plus 273. Okay, so I'm going to use my kelvins instead of my degrees Celsius. Okay, now it's a matter of putting it into my equation. So I know that I have P1 V1 over T1 is equal to P2 V2 over T2. Well, I have no pressure, so I get rid of that unit. And now I plug into my equation. My initial volume was 4 liters. My initial temperature was 297 Kelvin. And that is equal to my unknown volumes, that's my X, over 331 Kelvin. All right, so the easiest way to solve fractions is to cross multiply. That's exactly what I'm going to do here. So I'm going to end up with 4.00 liters times 331 Kelvin is equal to 297 Kelvin times X. Now I can go ahead and solve for X by dividing both sides by 297 Kelvin. So I'm going to do 4 times 331 divided by 297. So I end up X equaling 4.46. And my original volume was in liters, so this one is going to be in liters as well. Notice that our temperature increased, so our volume increased as well. All right, next one. Here it says the gas used in aerosol can is at a pressure of 103 kPa at 25 degrees Celsius. So we're starting out with a pressure and a temperature. So I'm just going to go ahead and start drawing my little chart to keep me organized. So my original pressure is 103 kPa, and my original temperature is 25 degrees Celsius. As if the can is thrown into a fire, what will the pressure of the gas inside the can be when the temperature reaches 928 degrees Celsius? So we have our second temperature, but the question is asking for the second pressure. Second pressure is X, and our second temperature is 928 degrees Celsius. Does not say anything about volume, so we can assume that it's staying the same. Again, we cannot have temperatures in degrees Celsius, so we're going to add 273 to both of our temperatures in order to get our Kelvin temperature. So 25 plus 273 comes out to 298 Kelvin. So that's the one that we're going to be using. The 928 plus 273 is 1,201 Kelvin. So that is the temperature that we're going to be using. So we always start off with our combined gas law. So P1V1 over T1 is equal to P2V2 over T2. Since volume is not being used here, it remains the same. We can go ahead and get rid of that variable in our equation, and we end up with Gay-Lussac's law with pressure and temperature. So I'm going to start plugging in my numbers. I know I have a P1, and that was 103 kPa, and my original temperature was 298 Kelvin. I don't have a second pressure, so that's my X, and then I have a second temperature, 1,201 Kelvin. Again, the easiest way to solve for numbers when you have fractions is to cross multiply. So you're going to end up with 103 times 1,201 is equal to 298 times x. In order to get x by itself, I divide both sides by 298. So I do 103 times 1,201 divided by 298. So that gives me a second pressure of 415 kPa. Again, it makes sense here because we know that the relationship between pressure and temperature is direct. So our temperature increased, so our pressure will increase as well. All right, last problem. Here it says the volume of gas of a gas-filled balloon is 30 liters at 313 Kelvin and 1.7 atm. What would the volume of the balloon be at STP? So I'm going to go ahead and fill in all of my knowns. So they gave me an initial pressure of 1.7 atm. They gave me an initial volume of 30.0 liters, and they gave me an initial temperature of 313 Kelvin. It says, what would the volume be? So we're looking for our second volume at STP. Remember, STP means standard temperature and pressure. So we need to go back to our reference packet. Again, I just took a screenshot of this portion of the reference packet, and it tells us that standard temperature and pressure are these units right here. So we always are using Kelvin, so 273 is going to be our standard temperature. So that's what I'm going to put in for my second temperature. And then pressure, since they gave us pressure in units of ATM, I have to make sure that my initial and final units of pressure are the same. So when I go back to my standard pressure, I have to make sure to pick the one that's ATM. So that's going to be 1 ATM. Okay, so I always start with my combined gas law. So P1V1 over T1 is equal to P2V2 over T2. I look at my chart and I notice that I have all of my variables here. So I'm using the full combined gas law. So now I plug in my numbers. I have 1.7 ATM times 30.0 liters over 313 Kelvin is equal to 1 ATM times X over 273 Kelvin. The easiest way to solve for fractions is to cross multiply. So I end up with 1.7 times 30.0 times 273 is equal to 1 ATM times X times 313. In order to get X by itself, I need to divide both sides by 1 and 313. All right, so in my calculator, I'm going to do 1.7 times 30 times 273, and then divide that by 1, which is the same, and then divide that by 313. So my new volume should be 44.5, and because my original volume was in liters, my new volume will be in liters as well.